Hey guys, so we'll be looking at Kirchhoff's laws for solving circuit problems. This is a way of solving circuit problems which uh, you'll find useful for solving certain kinds of problems involving capacitors and resistors. But right now we'll be discussing it from a capacitor's perspective, right? So let me start discussing the two laws first. The first law which you have is Kirchhoff's current law. The first law which you have is Kirchhoff's current law, which can also be called as KCL or junction law as well. It can also be called as KCL or it can also be called as junction law. And according to Kirchhoff's current law, imagine you have a junction. So this is related to a junction over here. So imagine you have a junction. By junction, you mean it's a point where you have many branches of current entering and leaving, right? So let me take it this way. Let charge entering this be Q1. Let charge entering this junction be Q2. Let charge leaving this junction be Q3. Let charge entering this junction be Q4. And let charge leaving this junction be Q5. Right, so according to Kirchhoff's current law or junction law, sum of charge entering a junction should be equal to sum of charge leaving a junction. Right, so in this context, it means Q1 plus Q2 plus Q4. These are the charges which are entering the junction, and that should be equal to Q3 plus Q5. That should be equal to Q3 plus Q5. And why is this law correct? Because we know that this is not a capacitor, so there can be no charge stored over there, right? So that is the idea behind Kirchhoff's current law. Total charge entering a junction will be equal to total charge leaving a junction. We'll be reading this more formally in current electricity. There you will see that instead of this being written in terms of charge, this can be written also in terms of current. So imagine that my currents are I1, I2, I3, I4 and I5. So there also you can write sum of current entering a junction will be equal to sum of current leaving a junction. The same idea as this, because you must not have any charge stored in the junction. So we'll have I1 plus I2 plus I4 is equal to I3 plus I5, right? So since you're discussing capacitors right now, you'll see this will be the one which is more relevant right now, but hopefully the idea behind the other equation is also clear. Okay, and then the other statement which we have is Kirchhoff's voltage law. The other statement which we have is Kirchhoff's voltage law, which can also be called as loop law or KVL. So this is called as KCL sometimes, Kirchhoff's current law. This is called as KVL sometimes or loop law. Right, and according to Kirchhoff's voltage law, let me write the statement first. Sum of potential differences across all elements, sum of potential differences across all elements in a circuit in a loop, across all elements in a circuit in a loop will be equal to 0. In a loop will be equal to 0. Will be equal to 0, right? So let me clarify what this means by taking a simple circuit. So let me take a very general circuit, that is a very simplified circuit. That is, I have a capacitor connected to a battery. I have a capacitor connected to a battery, right? Let the capacitance of this capacitor be C. Let the EMF of this battery be equal to E, right? So we already know that this capacitor will get charged up, and we also know what the charge on this capacitor will be equal to. But let's try to solve this by a different way. Let's try to use Kirchhoff's voltage law to get this value, right? So let me say that the final charge on this capacitor is Q. So according to Kirchhoff's voltage law or loop law, your sum of potential differences across all elements in a circuit in a loop will be equal to 0, which means start off from a point in a circuit and go in a loop. That is, go in a loop across a circuit, go in a loop across a circuit and come back to the same point. You can go in a loop either this way, either clockwise or anti-clockwise. That's up to you. But the main point is you have to come back to the initial point. And according to Kirchhoff's voltage law, sum of all potential differences across devices should be equal to 0. And hopefully the idea behind this is also clear, right? You're starting from this point and then you're going in a loop and then you're going in a loop and coming back to the same point, which means you must ultimately come back to the same potential. So when you add up all the potential differences across devices you'll be having, the total sum of potential differences should be equal to 0, right? Okay, so how would I be using it over here? So let me use Kirchhoff's voltage law in this case, right? So let me start off from this point. So let me go from here to here first. Let me go from here to here. So when I'm going from here to here, the element I'm going across is a battery, and I'm going from negative terminal of the battery to positive terminal of the battery, which means I'm going from lower potential to higher potential. So what will be the potential difference when I'm going across this device? The potential difference when I'm going across this device will be equal to EMF. That will be the potential difference across the battery. And since I'm going from lower potential to higher potential, the way I'll be writing the voltage law equation or the loop law equation over here is I'll say that my potential has increased by plus E. When I go from here to here, when I go from here to here, my potential has increased by E. So I'll write the voltage law equation as plus E, right? Okay, next I'm going from here to here. So when I'm going from here to here, I'm not going across any device, so there's no change in potential. So nothing to add in this equation. There's no potential difference right now, right? Next I'm going from here to here. That is from your positive terminal, your positive plate of the capacitor to negative plate of the capacitor. So when I'm going from here to here right now, I'm going from higher potential to lower potential. So my potential will decrease. My potential will decrease right now. And what's your potential difference across this element? Your potential difference across this element is nothing but potential difference across the capacitor. So that will be equal to Q by C. And I know that when I go from here to here, I'm going from positive plate to negative plate. So potential will decrease. So I'll say that my potential has decreased by Q by C. Right? So when I go, so let me again summarize this. When I go from here to here, potential increases by E. So plus E. When I go from here to here, potential remains constant. So no change in potential. When I go from here to here, potential decreases by Q by C. So minus Q by C. And then finally, I'm going from here to here. Again, I'm not going across any device. So there will be no potential difference. And now I come back to my initial point. So my sum of all these potential differences has to be equal to 0. And from this, I can find out what the charge on the capacitor will be equal. I can find out charge on the capacitor will be equal to C into E, which was, I think, something which you already knew from the way we solve questions in capacitors already, right? So this is one more way of solving this. So you'll see that these two laws are also ways of solving circuit problems. These are the most basic ways of solving circuit problems, though they are slightly lengthy. You will not be using it much, but they are slightly lengthy ways of solving numericals, right? So hopefully Kirchoff's voltage law and loop law is clear. In the next video, I will take up an example where I solve a question using KVL and KCL, using Kirchoff's voltage law and loop law. So please make sure you're going through this and please understand this properly, because this will be useful in solving circuit problems. See you guys in the next video.